Hello students, welcome back to the class of nuclear physics. I am Abhishek Kumar Chowdary, physics lecturer at Sri Chaitanya. In our previous lectures of nuclear physics, we have discussed the binding energy concept, mass defect concept, the constituent composition of nucleus, then the half-life, then the law of radioactive decay and average life concept. In today's class, we are going to first discuss the radioactive equilibrium, a very important concept, let me tell you. And then we will do some problems, some varieties problems on the topic that we have discussed in our previous class. So let's start with the radioactive equilibrium. First see this equation, this sequence you can see. A to B, B to C. We all know that there is a chain reaction going in radioactive decay, a chain reaction going in the radioactive decay. See, suppose at T equal to 0, A has the number of radioactive nuclei as N0. So A to B, so we can say A is disintegrating, but B is being formed. So formation of B and disintegration of A. Again, when we will see from B to C, then we can say C is being formed and B is being disintegrated. So, see here, at any time T, rate of formation of B, how rapidly, how quickly B is being formed, rate of formation of B is basically rate of disintegration of A. When A is disintegrating, then B is being formed. So B is being formed by A, and after formation, B is disintegrating to C also. So we can say rate of formation of B is rate of disintegration of A minus rate of disintegration of B. So in differential formula we can write dNB by dt is rate of formation of B. You can see here there is no negative sign, so here we are talking about the formation, not about the disintegration. This is a positive one. dNB by dt, rate of formation of B, is rate of disintegration of a lambda A Na minus lambda B by into Nb. dNB by dt, lambda A Na minus lambda B Nb. So basically in our previous lecture we only discussed there is a radioactive unstable nuclei and what is doing it is disintegrating. But to understand the principle, only disintegration is not taking place. It is basically a chain reaction. So first there is a disintegration, at the same time there is a formation, then that formation is disintegrating again. So this thing actually keep on going like this way. So again you can see the actual differential equation. At any time T, the rate of formation of B is rate of disintegration of A minus rate of disintegration of B. So this is the actual differential equation. Now on the basis of this differential equation, see, we can further solve this differential equation to get the equation related to what? Radioactive equilibrium. dNB by dt was what? Lambda A Na. Lambda A Na. Okay, so lambda is still there, but Na we can see at T equal to 0, it was N0. We can write it here, N0 at T equal to 0. So that Na can be written as N0 e raised to power minus lambda At according to the law of radioactive decay, the exponential equation that we got at the end, minus lambda B Nb. Okay. Now see this differential equation, dNB by dt was lambda A Na. But we know this Na, this is basically lambda A, this is basically Na. But Na, according to that exponential law that we got after the end of law of radioactive decay, the Soddy's and Rutherford's law. So this Na is N0 e raised to power minus lambda At minus lambda B into Nb. Okay. Now cross multiplying with dt and taking that negative sign into the left hand side, the equation is dNb plus lambda B Nb dt equal to lambda A N0 e raised to power minus lambda At. Now what we are doing to make a proper differential equation is multiplying by e raised to power lambda bt both the sides. Okay, and now this differential equation is being formed. In left hand side, the differential equation, differential form is for this. On right hand side, differential you can see in the term of t. But since exponential function is there in time, so this needs to be integrated. And after integration, this is a very important result. This, students, you have to remember a very important result in radioactive equilibrium. The raw result, there are many special cases on this basis, but this is the raw result. What is the raw result? What we are getting, first if you will see here, we are getting NB. And what was NB? NB was this. So A was decaying to B, B was decaying to C. So basically the middle one, B, NB, at any time T, what was the number of nuclei of NB? We know the formula earlier also, but that was only due to decay. But if decaying, the formation and decaying both are taking place, then at any time T, what is the number of nuclei? So that number of nuclei of B, NB, lambda A and not do remember is the T equal to 0 number of radioactive nuclei of Na. N naught is Na at T equal to 0. So lambda A and naught upon lambda B minus lambda A e raised to power minus lambda AT minus e raised to power minus lambda BT. This you have to remember. And what are the special cases? See. Generally, questions will be asked on the basis of the special cases. So that is basically a question for you. First is, we can see here, if average lifetime of A, TA, is far greater than the average lifetime of TB. And if you remember that average life is 1 by the decay constant, lambda. So if TA is far greater than TB, it means lambda is far less than lambda B. And if lambda is far less than lambda B, then what we can do, we can just put this as 0 and anything raised to power 0, students, is 1. So the equation is NB at any time T is lambda A by lambda B N naught, you can see here, and 1 minus e raised to power minus lambda B into T. So that is NB at any time T when the average lifetime of A is much greater, A average life is much greater than that of B. Again, there is one most common special case. In general, you will see the students in books, in numericals, they are using that second case that I am going to tell you now. Suppose we are dealing with some time T. The entire discussion is instantaneous, isn't it? At any time T, we have started with this. So now, if that time T is such that it is between the half-life of B and half-life of A. Now, we are talking about NB when at a time which is in between the half-lives of A and B. This is the inequality you can see. This is the inequality. Then in that case, e raised to power here, this one, e raised to power minus lambda bt, that becomes far less than 1. And if this one is far less than 1, this entire thing we are talking about, the entire function of exponent. If this is far less than 1, so what is left? Lambda a and not by lambda b. And in that case, this lambda a na is equal to lambda b and b. Cross multiply. And n naught was what? N naught was Na at t equal to 0. So lambda a na is equal to lambda b and b. Here we can write this lambda a and naught was there because n naught was this. But don't forget, n naught is nothing but Na at t equal to 0. So this is the most common form of radioactive equilibrium. Lambda 1 n1, lambda 2 n2. You most often will see this equation. But don't forget the actual time at which this equation can be applied. Because in competitive exams, if you are using this and time is not satisfying this, time is not obeying this, then your answer will be wrong. So this is the condition of radioactive equilibrium. This is the condition of radioactive equilibrium as well, both at different conditions. And what is the raw formula? This box. So I suggest you first remember this box formula and then the two special cases you yourself form by writing it. Now we will do some problem solving, the real test of the concept that we have discussed. We properly understood it or not based on numerical. See, before solving numerical for any chapter in physics, the analytical skill is very important. You have to, actually numerical is nothing but the numerical application of the concept you have learned. So before solving mathematically, you don't have to look at the data and thinking for the formula. You actually have to relate the each and every step for solving a numerical. Keep practicing this way. Numerical solving will be a very, very easy task. See, the first question. Find the number of half-lives elapsed before which 93.75% of a radioactive sample has decayed. While writing with the decay law of radioactive decay, the law is the decay rate depends upon the number of nuclei left. So whenever this is given the percentage in a question, this much percent or this much is decayed or this much is left, so there you have to see what exactly is left after that time. So that is, if we are talking about, you see, percentage, it means what? The actual was 100 and 93.75 has decayed. So number of radioactive nuclei left, we will calculate that first. Number of radioactive nuclei left, because in the equation of the decay law, the n is number of radioactive nuclei left. So that would be 100 minus 93.75%. Don't forget, here we are taking percentage, means here we are taking the original at t equal to 0 number of nuclei as 100. So this is what? 6.25. This is n, number of radioactive nuclei left. Okay, and original is 100. So students, what is n by n naught? This is simple, no? 6.25 divided by 100. And if you will calculate this, this is nothing but 1 by 16. And we have discussed one formula that half-life, n half-lives, that is n naught upon 2 raised to power n. After one half-life, this is n naught by 2. After second, this is n naught by 2, n naught by 2, n 1 by 2, that is n naught by 4, then n naught by 8. So after n half-lives, what is that? After n half-lives, this is n by n naught. After n half-lives, this should be 1 by 2 raised to power n. But here it is 1 by 16. So what is n? Obviously n is 4. Okay, so what question was asking? Find the number of half-lives. And number of half-lives is 4 here. So what you have to do, you have to just calculate n by n naught and equate it to 1 by 2 raised to power n, where what is n? N is for you number of half-lives. Number of half-lives. Formula, keep it in mind, n by n naught, 1 by 2 raised to power n, and if in a question given percentage decay left, always look for the what number of radioactive nuclei actually left. That was used in the decay law of radioactive decay. Now moving to the next question. Now see, this question is based on activity. First we will read the question, then again that analytical skill, what formula, how the stepwise relation of the formula, the mathematical knowledge of that concept, that is numerical. The activity of a sample of radioactive material is A1, okay, at time T1. So if you remember the activity formula, that was A is equal to A naught e raised to power minus lambda T. This is the activity. And what was the activity, students? It was dN by dt. The rate itself is called activity. So according to question, activity is what? Activity is A1, okay, fine, this is A1. And at what time? The time is T1. Again the activity is what? It is A2. So A2, and what is this? A0 e raised to power. At what time? Time is T2 again. Minus lambda into T2. The activity of a sample. So activity is changing, but sample radioactive, one sample is there, so the lambda will not change. One mean life, one lambda, one decay constant. Okay. Obtain an expression for its mean life. Okay, fine, mean life is required. So what we exactly want is 1 by lambda. And from here we have to calculate 1 by lambda. So do one thing. This was our equation 1. This was our equation 2. First take A1 by A2. A1 upon A2. See what is there. A0 will be cancelled obviously, and it will be e raised to power lambda T2 minus T1. Moreover, in the question you can see it is given also T2 is greater than T1. E raised to power minus lambda T2, it will go into the denominator, and by solving in numerator it will be positive. Okay, this ln A1 upon A2 is equal to lambda T2 minus T1, and ln E is 1 here. ln E is 1. Let me tell you one thing. For solving the concept of radioactivity, a basic knowledge, base change, and that coefficient becomes power becomes coefficient concept. I want you to say that the basic knowledge of logarithm, not much depth knowledge, but basic knowledge of logarithm is much needed in solving this. So here lambda is 1 upon T2 minus T1 ln A1 by A2. Okay, and what was required? The required was mean life. So what is mean life? 1 by lambda. So from here, from lambda we can calculate mean life as T2 minus T1 upon ln A1 upon A2. This is 1 by T2 minus T1 ln A1 by A2. You will get this. So that further final solving is not that something to learn, but learning what? If activity is there, what we have actually, we have to find out how to go step by step there, and the basic knowledge of logarithm. Do write it down. If you are comfortable in logarithm, it's okay, it's good for you. If not, for solving that decay radioactive constant questions, do strengthen your logarithm concept. Okay, moving to the next question. This question we are going to solve on the basis of parallel emission. It means some sample is decaying with the two decay simultaneously. That is, there is an alpha decay as well as there is a beta decay, but these are not one by one, rather they are simultaneous. In such cases, we have learned the concept of parallel emission in our previous discussion. In such cases, the lambda equivalent for that decay is lambda 1 plus lambda 2. Basically, the half mean life is related as 1 by tau is 1 by tau 1 plus 1 by tau 2. Like this, 1 by tau is 1 by tau 1 plus 1 by tau 2. And you know that what is this tau? What is this mean life? 1 by decay constant. So we can say here that lambda is equal to lambda 1 plus lambda 2. It means in this question, now we will read the question first. Mean lives of a radioactive sample are 1620 and 405 for alpha emission, you can see, and for beta emission. Means, see, mean lives is related to the decay constant. And the decay constant lambda is related to the decay. So if a certain sample is decaying by two different decays, it means it has got a mean life for each decay. This is a very fundamental of radioactive decay. Alpha emission has got its own mean life. The radioactive sample has a mean life for alpha decay, it has a mean life for beta decay. So in this question, both the mean lives have been given for alpha and beta. Find the time during which 3/4 of a sample will decay. It means 1/4 will left. Again, we are talking how much is left. If given is this much has decayed, we will be interested in only how much is left. So 1/4 will be left. And if it is decayed by both alpha and beta emissions simultaneously, this is the important word. And we are discussing the concept of parallel emission in this solution. So lambda 1 plus lambda 2 is what we used in case of simultaneous decay. So lambda is lambda 1, that is 1 upon 1620 plus 1 upon 405. And on solving, this comes out as 1 upon 324 years. Here, 1 by per year. This is the lambda, okay. First, we have done with the lambda, we have calculated lambda. So do remember, for a simultaneous decay, what is the lambda? Lambda 1 plus lambda 2. And how it came? This. 1 by mean life is 1 by tau 1 plus 1 by tau 2. Now using the formula, n is equal to n naught e raised to power minus lambda t. This is the exponential formula for the law of radioactive decay. And don't forget, what was n? N was left or decayed. N was left. So n or n by n naught is 1 by 4. Since 3 by 4th have been decayed, so what is left? 1 by 4, and this is equal to e raised to power minus lambda t. Taking log for both the sides, minus ln 4 is minus lambda t ln e, and you know ln e is 1. Again, I have to say that for solving radioactive decay constant, and let me tell you, these questions are quite frequent with the NEET exams. So you have to be very strong in the fundamentals of logarithm. ln 4, that can be written as 2 ln 2 is equal to, minus is cancelled here. This is lambda into t, and we know lambda. So the t is 1 by lambda. So lambda was 1 by 324. 1 by lambda will be 324 into 2 ln 2. We can put the value of ln 2 as 0.693. That depends in what format the option is there. But again, in this question, what is the learning? First is this: for simultaneous decay, lambda is lambda 1 plus lambda 2. And for solving, this is logarithm concept. And last but not the least, in law of radioactive decay, n is the number of radioactive nuclei left. Okay, now the next question is, you can see anti-graph, and that graph was exponential graph. If you remember, n equal to n naught e raised to power minus lambda t. Exponential decreasing, that was for the number of radioactive nuclei left. For number of radioactive nuclei decayed, there was a graph exponential increasing. Okay. So on the basis of this graph, let's see what question is asking. Graph shows the variation of radioactive nuclei left undecayed with time. Find the time corresponding to n equal to n naught by 3. This is the n naught by 3, and the corresponding time is t1. So basically we have got what is required, and that is t1. Fine. But okay, if this is required, it means this t naught corresponding to 2n naught by 3 is given. This is known to us. In objective question, they might give you t naught as 2 second, t1 as a required value, and not as some numerical value. So we are solving this question in the form of denotions only. See, this is exponentially decreasing graph, and for radioactive nuclei left, n is equal to n naught e raised to power minus lambda t. This is the standard equation, exponential equation for number of radioactive nuclei left. Fine. Now if n I am taking 2n naught by 3, 2n naught by 3, This is n naught. So obviously time I will take as t naught. Okay, this is cancelled. Taking log both the sides, ln 2 by 3, that can be written as minus ln 3 by 2. Again, basic concept of logarithm came. So if in log we are writing log ln 1 by x, that becomes minus ln x, the fundamental of logarithm, is equal to, the power becomes coefficient, that is minus lambda t naught ln e. And what is ln e? We know ln e is 1. Obviously the negative signs will be cancelled, and lambda is equal to 1 by t naught ln 3 by 2. This is a question in itself. Suppose there is an objective question, so they might ask you the decay constant also, or the mean life also, that is 1 by lambda. So this is a one question in itself. Now moving to the actual requirement, and that is obviously T1. So corresponding to T1, what is n? N naught by 3. Again by using this formula, n is n naught by 3 is equal to n naught e raised to power minus lambda T1, and T1 is required now. Again taking log both the sides, we can write minus ln 3 is equal to minus lambda T1. And don't forget, because ln e is 1, you have lambda now, and T1 is required. So what is T1? T1 is ln 3 by lambda, and ln 3 upon, what is lambda here? 1 by t naught ln 3 by 2. This is the final T1 that we solved on the basis of the exponential graph and exponential equation. So we have done with the concept of radioactive equilibrium, and we have seen some questions based on the law of radioactive decay. In previous classes also we have done the mass defect and binding energy questions. In today's class, what conclusion we are getting? As a student, what you have to get, what you have to be prepared for learning the radioactivity is the fundamentals of logarithm, and you have to actually understand the values of the variables, what is n, what is lambda, how they are related. If you will see, the questions are not that difficult. Some similar questions you will see in the competitive exams also, but practice is very important. In this nuclear physics concept, the numerical, when we are talking about numerical, practice is very important. Otherwise, what it will take, you will be able to solve a question in more than 1.5 minutes in NEET. And that is not the case. Taking a longer time for solving a question is equivalent to no solving at all. So in our next classes, we are going to discuss rather more interesting concepts. There are nuclear fission, nuclear fusion, nuclear reactor, breeder reactor, proton-proton cycle. Many interesting facts are yet to come. So in the world of quantum mechanics, we are right now in midway in nuclear physics. So we have to go to the other side also. So we will discuss the entire concept, but I want you all students to solve as many questions as you can solve on the topic we have discussed. All the best, happy learning, God bless you, bye bye.